complexes and hydrogels. So abandoned mine drainage is one of the second highest causes of water pollution in PA. It results from water runoff from abandoned mines and mine waste, and it leads to an increase in acidity in a body of water and an increase in concentration of dissolved metals. I unfortunately did not have time to look at the pH aspect of this, but I did look at the transition metal pollution aspect. So transition metals are D-block elements that have multiple oxidation states, and transition metal pollution is bad because these metals can accumulate in plants, fish, and other organisms. Some transition metals are biologically essential, like copper, iron, but they can be toxic at high enough concentrations. Okay. So in terms of transition metal remediation methods, there's reverse osmosis, there's stuff you can do with membranes, but I was mostly focusing on adsorption for my senior research. And so there's a couple different adsorption methods down here. Flocculants, hydrogels, chelators, zeolites, etc. Okay, so the molecule that I synthesized for my senior research was ZW3. So basically this is a SNAR reaction between an electron-rich nucleophile and a polynitroaromatic group. In that case it was picric acid. Okay, so let's go to, oops. Okay. So what does this have to do with transition metal remediation? So ZW3 actually has this negative charge distribution all over the molecule, which allows it to bind to cations. And it can also bind to anions, but I was mostly focusing on this aspect. Okay, so in terms of applications, in the literature so far, ZW3 has been used for fluoride detection and absorption. It's been incorporated into a metallogel. It's been used for oil adsorption and metal ion absorption and detection. Okay, so far in the literature, the absorption techniques for ZW3 in terms of transition metal removal have involved sonicating the polluted water with the Zwitterions in the solution, and then loading the Zwitterions onto a column and then running the polluted water through the column. And so the goal of this project was to instead incorporate my Zwitterions into a hydrogel matrix for enhanced metal ion absorption. And so this is a little background on hydrogels. So hydrogels are hydrophilic gels. They're 3D cross-linked polymer networks, and they absorb large amounts of water without dissolving in solution. And so they're really flexible, and they'll swell until the equilibrium is reached between the osmotic pressure of the water going in the network and when that balances the elastic force of the network here. So this is the dry gel. It's kind of like crunched up, and then this is after it's exposed to water. It swells up really nice. Okay, so the goals for this project were to, 1, synthesize and characterize ZW3. The second goal was to perform binding studies and swell ratio tests with different gels, so I could have a gauge of how the matrices that I'd be incorporating the Zwitterions into would perform just by themselves. And then I wanted to find a formulation that would work to incorporate the Zwitterions into a gel. And then I wanted to perform binding studies with that composite gel. So here I have a little schematic. This is my Zwitterion. This is a hydrogel network. You can see there's cross-linking here. And then I want to take those two, combine them into a composite material for enhanced absorption, because theoretically the hydrogel network is hydrophilic. It should encourage water to come into the network swell, and then the Zwitterions inside the network should catch the metal ions. Okay, so I'm going to transition back to my zwitterions and the synthesis process. So this was my crude product, and I think that the IR spectra from my crude product are the strongest piece of evidence I have that I synthesized the correct molecule. So this is my crude product, and you can see there's this really prominent peak here around 2000. This is the C double bond N peak from the DCC. And then this is after one chromatography column, so you can see very nice, colorful, tedious column here. So this is after one column. You can see it's kind of less oily, not as dark. And then this is after three columns, and you can see that this peak from here has completely gone away. And it doesn't look as dirty as that one, so let's see. Okay, and then I just wanted to show a reference spectra from the literature. So this is a reference spectra of ZW3 from a research paper I found. And this is my spectra, and it looks pretty darn close, which is good. So, okay, and then just to make sure that I synthesize what I wanted to, I compared the wavelengths or the UV vis spectra to the literature, and it did align with the literature. At least the pure product aligned with the literature. The low purity product was shifted down a little bit in wavelength. And then this is the fluorimeter scan, again, just to be thorough and make sure I actually synthesize the correct molecule. And then this is my proton NMR. So something you'll notice is it doesn't look as nice as the product on the last few slides. It's not like that nice bright red color. It's so this, I actually took this semester, and it turned a different color, and it wasn't crystalline anymore. So as you can imagine, the proton NMR isn't the best. So my integration suggests that there's 130 protons in the molecule. So there's actually only supposed to be 47 protons, which is problematic. But again, this was a semester later, and something probably happened to it over that between winter break. And so there actually should be a singlet here at the 4 ppm range. This is not a singlet. And there's these peaks here that don't show up in the literature, so I'm not really sure what that is, but it's not supposed to be there. And then this blob right here is supposed to be the cyclohexyl groups on the molecule. Okay, and now back to the gels. So again, before incorporating my zwitterion into the gels, I had to find a decent formulation and do some testing with gels in terms of like binding, absorption, swallow ratio. Oops. Sorry guys. Okay, so the first gel formulation that I tried out was a sodium acrylate and acrylamide copolymer. So these are my two monomers. This is acrylamide, sodium acrylate, and this is the cross-linker, diethylene glycol diacrylate right here. This is my initiator. And so once I mix them together, I put them in the oven, and then they kind of just solidified like that. Okay, so for the absorption test I ran with the sodium acrylate and acrylamide gels, what I did was I dissolve different metal salts into a solution, so I'd have a spiked solution to test my gels against. These were actually supposed to be 10 ppm, but I'll address that issue later. So I weighed out about a gram of each gel. So this is A, B, C, and D, and then this is my control. And so these are the spiked solutions, and so I introduced each of the gels to the spiked solution, and then I set them on a stir plate for 24 hours, and then over time I took out aliquots from the solution, and then I measured it on the MPAES. And so for the swell ratio test for the sodium acrylate and acrylamide gel, what I did was I weighed out the dry gel. I weighed out about a gram of gel, and then I set it in water for 24 hours. And then I weighed that, dried it, and then I calculated the swell ratios. And you can see that I use different formulations for gels A through D. So this has a 1:2 ratio, sodium acrylate to acrylamide. This is a 1:1, 2:1, and so on. So see that gel D had the largest swell ratio. Gel C was kind of in the middle. B also kind of in the middle, and then A had the lowest swell ratio. Okay. And these are my results from the adsorption test with my hydrogels. So this is the percent ion removal over time. So this was my first attempt at doing these absorption tests, so the range initially wasn't that great, but you can kind of see this trend where the gels absorb, they start to absorb stuff out of solution, and then it kind of tapers off when the gel and the ions equilibrate. Okay, and you can see that A and B, they appeared to remove more than C and D, and that, going back to the swell ratio, D has a greater swell ratio, which means the network is going to be expanding more, and so it might not be able to hold on to those ions as well as A or B. Okay, and magnesium shows a similar trend, and then these bars underneath the y-axis, I'll address them later. That was another issue that popped up. Okay, manganese, A and B performed pretty decent against manganese. C, it was so-so, and then D, didn't really do much. And then zinc, it's a similar trend with the manganese. A and B did well, these two not so well. And then copper, none of them really, well, initially it looks like they absorbed some copper, but then after that it just kind of either went back into solution or something. Okay. And then, yeah, so the gel, like I said before, gel D has the, what did I do? Okay, gel D has the greatest swell ratio, and, oh my god, I forgot to, okay. So this is their sodium released over time because one of the monomers in the polymer was sodium acrylate, so it's expected that once it's in solution, it's going to release some sodium and exchange ions for sodium. So D had the greatest swell ratio, released the most sodium. A had the smallest swell ratio. Well, I think that this is a dilution error, but it looks like it's releasing the least sodium. And so the swell ratio is going to be dependent on the formulation I used. And yes. Okay, so based on the trends from those percentage removal plots, so it appears that the selectivity for the sodium acrylate acrylamide gels is preferred to bind with calcium and magnesium over manganese and zinc, and then not much copper. And that, I would have to calculate the KD to confirm that rigorously, but that's just what the trend appears to show by the percent removable. And so the gels with the smaller swell ratios performed better than the ones with the larger swell ratio. So A and B did the best across all the categories. And the reason for this, the absorption with the gels is because these C double bond O groups on acrylamide and sodium acrylate are, according to hard soft acid base theory, it's a hard base, and hard bases like to interact with hard acids. And calcium and magnesium happen to be hard acids. These three are borderline, so it's going to want to interact with these two more. Okay. Now the gels modified with the chelating agents. So chelating agents basically coordinate with the metal ions in solution and help you remove them. And so I performed a similar absorption test with these guys, except the initial concentration was a little bit different, and I used 0.1 grams of the gel instead of 1 gram, which was an experimental error on my part. And so, okay, and these are the results from the chelating agent modified gels. I had a larger time range this time because I was more used to the absorption tests. In terms of percent removable, it doesn't look like they're performing as well as the other gels, but again, there's other more rigorous ways to evaluate that, different absorption models that I could have looked at, but I didn't have enough time to do that. So magnesium, and then there's manganese, which they perform decently against with the percent removable, and then there's zinc, and that was good. Copper, again, not so good. Okay, so the trends for the chelating agent modified gels, so it appeared that these guys all were removed at the same percentage, the calcium, magnesium, manganese, and zinc. The copper still wasn't removed that well. And so I was kind of surprised that the chelating agent didn't remove more of the metal, or that it seemed to prefer to remove calcium and magnesium because, well, the stability is supposed, from the literature says the EDTA metal complex is supposed to be low transition metals greater than calcium and then magnesium. And so I assumed that the transition metals would see a greater percentage removal over time, but they didn't. And so, yeah, okay, so in terms of sources of error, there were a couple different areas where there could have been error, or there were error. So all the analyte concentrations were actually supposed to be 10 ppm, so I wanted a 10 ppm spike solution with 10 ppm sodium, or not, calcium, copper, magnesium, whatever. And the salts that I used to make my standards were not dry. Some of them were kind of hard actually, so the concentrations that I calculated were different from what they were supposed to be. And also the beakers weren't covered in the hood, and you can see how this concentration kind of like increases when it's not supposed to. Like my initial concentration, this is my final concentration. The final concentration shouldn't be higher than the initial because that's not possible. Okay. And also copper was half the concentration of the other ions, so that could explain why it didn't get absorbed as well, because there's not as much of it to it could be more easily outcompeted for binding sites. Okay, more sources of error. Again, like I mentioned, for gels A through D, I used 1 gram. And then for the chelating agent modified gels, I used 0.1 grams. So that's an order of magnitude, that's about an order of magnitude difference. And so the mass is important. The amount of the adsorbent you use is important because it affects the surface area, it affects the amount of binding sites available, and it affects the maximum concentration before your adsorbent becomes saturated. And so you can see this is the adsorbent dosage here. So this is the mass of adsorbent per volume. So I used 100 milliliters for all of my tests. And you can kind of see how different this is. So it really wouldn't be fair for me to say, well, I wouldn't want to make any conclusions about which one's better because, well, I didn't even use the right amounts of the gel, so, okay. And now, once I made the zwitterions and I did some absorption tests, I decided I'm going to try to incorporate the zwitterions into a gel. And so I tried to incorporate the zwitterions into this sodium acrylate acrylamide gel that I was testing with the absorption test. But it didn't work because the zwitterions are really non-polar because they have those huge cyclohexyl groups all over the molecule, and so couldn't incorporate into the gel, and I had to extract this with DCM to recover my product. Okay, and then this was the second attempt at trying to incorporate the zwitterions into the gel, and so ZW3, it was initially miscible in this HEMA T-butyl acrylate polymer, but once I put it in the oven, the polymer started to phase separate out of solution. You can see how it's kind of chunky and there's white stuff in there. It shouldn't look like that. So I'm assuming that what happened is that as the polymer grew, once it was in the oven and the initiation kicked off, that once the molecular weight started to grow, cross-linking increased, that the solubility of the polymer in the solvent decreased, and then there were less favorable interactions, and then everything crashed out. Okay. And then this was my final attempt at incorporating the Zwitter ions into a gel. So in this reaction mechanism, I used bisphenol A diglycidyl ether and branched polyethylenamine. And I basically just plopped them into a pie pan and started stirring them, and it worked. Yeah, ZW3 was able to homogenize into my copolymer, and so I just assumed, well, there must be favorable interactions between the two monomers and the Zwitter ion. And you can see the molecular weight of this and how long these chains are. It makes sense that these are kind of like long nonpolar chains, and ZW3 is really hydrophobic, so I guess it makes sense how they can mix in together better. Okay, and this is just a summary table of the different formulations I tried. So you can see the first three methods did not work, but this one did. Okay, yeah, so another summary. None of the gels were able to absorb were able to retain copper after 24 hours. Gels A through D had a greater percentage removal for calcium and magnesium over zinc and manganese. The gels modified with the 8-hydroxyquinoline and cyclohexyl EDTA had a similar percentage removal for calcium, magnesium, zinc, and manganese. ZW3 was successfully integrated into a hydrogel finally. And in terms of practical use for the gel, this is very early in our method development phase. So really, right now, it's only good for benchtop metal ion removal. It's not going to hold up against like thousands of gallons a minute of water going through a mine. And since it performed well against calcium and magnesium, it could be a water softener or something like that. Okay. And so future steps, if I were to continue this project, I would try synthesizing the analog that has the isopropyl groups instead of the really hydrophobic cyclohexyl groups, because that should hypothetically be easier to mix into a hydrophilic gel than something with huge hard groups. And I'd like to perform more binding studies with different gels and move from millipore water to actual polluted water. And so I forgot to add an acknowledgement section, but I do want to thank Dr. Fish for being a great advisor, and the whole chemistry department, and Miss B for making sure that I have the MPAES turned on.